All right, welcome back. Hope you had light enough lunch so that you can stay awake. So let me introduce our next speaker, who is Vatsal Sharan from USC. So I didn't know Vatsal until 2 years ago. And typically, as I keep telling people, market forces are the most excellent way of knowing everything. So how did I get to know of him? He's a student who was working with me, decided one day to tell me that I'm not going and joining Adam Weirman. Hopefully not watching. So he had an offer from Caltech to do his PhD, and he suddenly told me that I'm going to go and work with Vatsal. I said, "Who is Vatsal?" I had no idea. Even though I was writing a recommendation letter for him, I did not all know where all he was applying. And then I looked up what Vatsal is up to. That's how I get to know him, and now you will get to know him, what he's up to. So Vatsal got his PhD from Stanford, and is faculty at USC right now, where he tries to understand how learning and life works. He's made a teeny bit of progress on the former, but none on the latter. And he also likes to run, meditate, and eat. So hopefully Mumbai provides a good enough opportunity to eat. So with that, let me invite Vatsal to give it.
Thank you so much, Rahul, and thank you all. Thank you all for coming, and I had a great time in the talks in the morning. Can you all hear me okay at the back? Okay, great. Yes, the talk after lunch. You all must be a little bit sleepy. I think I've kept it pretty high level, so hopefully it's not too technical. But please feel free to stop me at any point, ask questions. We can make this interactive. We have 2 days, so we don't need to go through any amount of material today. So I'll talk about using memory as a lens to understand efficient learning and optimization. So just to set the stage a little bit, at a very gross level, if you think of machine learning as some kind of box, some people might call it a magical box. So it's a box which harvests an impressive amount of compute and an equally impressive amount of data which is raining down on it to then solve some interesting and important problems. Then if machine learning is this box, then at the heart of it is really optimization techniques. So optimization techniques are the main workhorse of modern machine learning. They are really our main algorithmic suite that we have. And broadly, my goal here will be to talk about some perspectives on understanding how information and computational resources interact for optimization and also learning more broadly. So if you go back to this toy picture, then like the two most basic resources here are really like the amount of compute that you have available and the amount of data or information that you have available. And my goal here will be to try to understand the interaction between the two. So are there trade-offs between these different resources? And I'll be using memory as the main computational resource. So that will be the main metric that I'll use to understand what is efficient and what is not. So let me tell a little bit about why I think that is interesting. So first, like in theoretical computer science, memory has been a fundamental computational resource. Like even if you go back to the Turing machine, like the two most important resources are the length of time that the Turing machine runs for and the length of the tape that it uses, which is the memory. So really like time and memory, they are like the two most fundamental resources. It's important just from a theoretical perspective to understand learning and to understand how computation works. But increasingly, in many modern practical settings, memory is the main bottleneck. This is due to a lot of reasons. We often want to run our models on devices with small memory. We want to have models which are as large as possible because in general, large models seem to do better. So this is some figure which tells us how kind of the GPU memory limit has determined the largest models we have. And whenever we have models with GPU chips with more memory, we usually build and go off and build larger models which can exploit that memory. And obviously with large models, we need a huge amount of data to train these models, which also requires a lot of memory. And even at a high level, apart from these specific reasons, I think what we've just seen in computer science over the last like 3-4 decades or even longer is that like due to Moore's law, we've had computation advance at a very rapid pace. Like every 1.5 years or so, we have this doubling. And due to that, like computation has increasingly become very cheap. On the other hand, the memory doesn't grow as quickly. So obviously, we've had a lot of increase in the available memory from like the last 50 years to now, but not nearly as much as the amount of compute that has grown. So, for example, like the last 20 years or so, the hardware floating point operations per second, they scale at roughly like 3x every 2 years, whereas the memory and like the memory bandwidth increases by like 1.5 or so. And when you combine all of this with various software optimizations like multi-threading or parallel processing, what we are often seeing in many modern applications is that the actual compute itself is really cheap. And we are used in theory to think of the number of steps of an algorithm as the proxy for the running time. Usually we don't even distinguish between the two, right? Like running time, we just think of it as the number of steps that the algorithm runs for. But in many modern settings, I think like the realities right now are very different. Like there's lots of other constraints which determine how efficient things are actually in practice. And increasingly, like the memory limitation that you have is a major bottleneck. And it's true even for energy usage too, because if you have limited memory, then you need to move data from one chip to another, and data movement is one of the biggest uses of energy. So in many modern settings, I think especially like in ML applications where we've had these chips which are really good at doing computation. So matrix computations are super cheap now. Like it's really, in most settings, we are not at the point where the number of floating point operations is the main bottleneck. It's really like how much memory can you use, how much can you fit in memory, how much do you need to move things around. So for this reason, like we have memory as like a primary bottleneck in many settings. And so from just a practical motivated standpoint as well, I would like to understand what role memory plays in learning. So, so memory is a fundamental computation resource that's crucial in practice. And my talk will mainly be around the role of memory in learning and optimization. In particular, there are trade-offs between the available memory and the required information to learn. And we'll talk about a few different settings like gradient queries or number of data points. And I think an interesting phenomena that seems to be happening in a lot of settings is that there appears to be a pretty sharp dichotomy in the algorithmic landscape. So what do I mean by that? So it seems that in many settings, if you look at the algorithmic landscape, there are some memory efficient techniques, and I'll talk about them. Usually these are variants of gradient descent. And then you have techniques which are much more memory intensive. And often there's not much in between the two. So in many settings, it seems that you can't really improve on the convergence rate of these memory efficient techniques without using a lot more memory. So a strict separation somehow, which I find pretty interesting. And still pretty vague at this point, but I think it'll hopefully become clearer when I instantiate this in a few different settings. So I'll talk about maybe three things. So I'll talk about first optimization with access to a gradient oracle, the first order oracle. Then I'll talk about stochastic optimization and how we can use some of these perspectives to understand how transformers solve linear regression. This will be a bit more applied. And finally, I'll talk about detecting certain planted structures, solving things like planted clique in a streaming setting. Any questions before we proceed? Okay, cool. So let me start with the first part. So it's really the canonical optimization setting. So you're trying to minimize a convex Lifshitz function and over, say, the unit ball. And you have access to a first order oracle. What does a first order oracle do? You can query the oracle at any point, say x, and the oracle will reply with the function value at that point f of x and the gradient at that point, the grad f of x. And your goal is to try to minimize this function given access to this gradient, this first order oracle. It's a very well studied setting, and the most basic algorithm that one could think of here is just gradient descent. Just that's the obvious thing. We are all familiar with it. You initialize at some point, and at every query point, you query for the gradient, and then you step in the direction of the negative gradient. Keep doing this, eventually you converge to something close to the answer. Okay, so let's look at how efficient this is. So we're solving this problem in d dimensions. Claim that it uses order d computation time per query if we have access to this oracle. So this oracle is giving us the gradient. We don't have to worry about implementing this gradient oracle. If you have access to the gradient, then the update is just a linear step that takes only order d computation time, d dimensions again. You also only need order d memory. You're not storing anything apart from your current iterate at x of t. So you don't need to store any other extra information. So just order d memory. And you can look at the query complexity. It can be large with respect to the desired error epsilon. So if you want a point, if you want to find a point which is epsilon optimal, you need 1 over epsilon squared queries. That's the convergence rate that you get with gradient descent. Okay, what else can we do? There's a suite of other techniques. Roughly, they are based on like the ellipsoid algorithm, center of mass. You don't need to be familiar with these things. They do something like a high-dimensional binary search. They split the space up and like doing something like binary search in high dimensions. So the main thing is that these are a lot more expensive. They need more than quadratic computation time per query. They also need a lot more memory. They need to store a lot of previous gradients. So typically, these methods will require quadratic memory. But using this extra memory and computation time, they can get a faster convergence rate in terms of epsilon. So to find an epsilon accurate point here, these methods only need d log 1 over epsilon queries. So if you're looking at like small enough epsilon, this could be much faster. You're essentially getting an exponential speed up in terms of the convergence rate for epsilon. Any questions here? Okay. So our goal here is to understand if these complex algorithms are necessary. What do I mean by complex? You could consider different metrics. So for example, gradient descent and all of its variants, like they're just like much simpler. I can describe the whole algorithm essentially in these 4 lines, whereas I can't really do that with these more complicated techniques. And that's probably a big reason why like gradient descent and all of its variants, they are much more popular. Like they're simple, easy to maintain, easy to run. That's one metric that you could think of. You can look at computation time. Like here you need order D computation time per query. On the other hand, with these other techniques like ellipsoid and so on, you need quadratic computation time. And you could look at the memory usage. Here you only need linear memory again, whereas versus like with these other algorithms, you need order D squared memory. And as I said in the beginning, we'll use memory as the main metric of computational cost to distinguish different algorithms. And I think it's interesting that, and this is true here in a lot of other settings as well, it seems like complexity along one axis seems to mirror complexity along different axes. So for example, I don't think it's a complete coincidence here that things which use less memory also are efficient in terms of the running time, and they're also a lot more simpler. And this seems to be true in a lot of different settings. It seems like certain problems which are hard, they seem to be hard with lots of different metrics as the metric of computational cost, be it running time, be it memory, and so on. And the good thing about memory is that in many cases, we can show separations between these different techniques, what you can do with, say, order D memory versus more memory. So these separations would be much harder to show for something like running time, like just because we don't really have techniques to show unconditional lower bounds for running time. Like these in some sense, it would be stronger than separating P versus NP without getting into too much details. So just to back up, we'll be using memory as the main metric of computational cost, which seems to mirror and match efficiency along different axes as well. So if we look at memory here, what we really want to understand is if there are some inherent trade-offs between the available memory and the information requirement. So if you look at some graph where memory is on the x-axis and the information requirement in terms of the number of gradient queries is on the y-axis, we want to understand which points here are algorithmically feasible. What can we hope to realize? Let me make this a little bit more formal. So same thing again, but being a bit more rigorous. I plot memory in terms of the number of bits that are used, and I plot the information requirement in terms of the number of first order queries, gradient queries. So gradient descent, it needs D memory, and it gets this 1 over epsilon convergence, 1 over epsilon squared convergence rate, which I mentioned earlier.
One question.
Yes.
You studied to count bits.
Yeah. Yeah. So it's actually should be D log 1 over epsilon bits. So I'm not worrying about that right now. But yeah, there'll be some log 1 over epsilon in terms of the bits, which I'm ignoring here for simplicity. And with that, you get this 1 over epsilon squared convergence rate. And you also need D memory, just because the answer is D-dimensional. You're solving the minimization problem in D dimensions. So you need D memory just to even store the answer. So everything on the left of this line is not feasible. That's all in red. That's just information theoretically not feasible. On the other hand, we have these cutting plane-like techniques, which I mentioned. These use quadratic memory. They can get a faster convergence rate in terms of epsilon, so D log 1 over epsilon queries. And we also know that this region over here is also not feasible. So you cannot get a faster rate than d log 1 over epsilon. And this is not trivial. This comes from like lower bounds from an optimization from Nemirovsky back in the 80s and so on. But like this is known to not be possible. You cannot get a faster convergence rate than d log 1 over epsilon. And so this is all in red. Over here, this is in green because obviously if you can get this, you can also get something over here. You just waste your memory, waste your queries. So that point is, all of those points are trivially possible. And we want to understand if there's anything in the middle, like what is possible. So what is known about this? So there's a long line of work on information theoretic lower bounds and optimization, which I mentioned before, which tells us just the number of gradient queries which are needed to solve an optimization problem up to a given accuracy. And this has been really influential in helping design optimization algorithms, but it only looks at the information theoretic cost again. So it just looks at the number of gradient queries without worrying about the complexity of the algorithm in terms of running time or memory or whatever notion you want to look at. So if you look at memory, there are memory lower bounds for streaming data in online settings. So a lot of this work is for worst case data streams. There's been a very interesting line of work on memory lower bounds over stochastic streams. A lot of it is over finite fields, things like parity, which are interesting problems, but a little bit farther away from practice, the kind of things we are interested in machine learning. There's not, prior to this at least, there was not that much in terms of memory lower bounds for optimization. And that's where this work comes in. This is based on joint work with Annie Marston, Aaron Sitford, and Greg Valian. And what we show over here is a trade-off. So here's the result. So just read through it slowly. So we show that for a certain epsilon, it's like some desired error epsilon, which is like 1 by poly d, like something like 1 by d to the fourth. And for any delta, any constant delta in the interval 0 to 0.25, any algorithm, even if it is randomized, if it uses memory d to the 1.25 minus delta, so uses less than this much memory, then it requires at least d to the 1 plus 1.33 delta first order queries. So let's look at this plot again, just to help us understand this. So what this is really showing is that there is some region here in this trade-off curve which is not feasible. So if you have less than this d to the 1.25 memory, then you cannot get this optimal query complexity. You would need more queries. And in this linear memory regime, you need like d to the 1.33 queries. So it's showing that there is a trade-off and you cannot get the fast, efficient convex optimization rates without using some super linear amount of memory at least d to the 1.25 memory according to this bound. Any questions about this?
So we find a class of bad convex functions.
Yes, yeah, we construct a class of bad functions. I won't talk about it today, but tomorrow I'll hopefully talk a little bit about it, like how the construction actually works. But it has to be a class of functions. And like for this class of functions, like we show that you cannot, memory limited algorithms cannot get this rate.
There's also a third axis that you are not considering. Time complexity.
Yeah, you could consider like a 3D plot if you wanted to as well. We are not considering that here.
Is focusing.
Just that slice through that 3D curve. Yeah. Any other question? And I'll talk a little bit more about the proof techniques maybe tomorrow. So we showed this lower bound up to this d to the 1.25 memory. After that, there were a lot of interesting results, which actually improved it all the way to d squared for certain problems, like under some additional assumptions compared to this result. But at least in certain settings, we know that you actually need all the way to d squared memory. So these d squared memory techniques, they are Pareto optimal in the sense that you cannot get their convergence rate without reducing with less memory usage than what they use.
Also applies to the linear program.
Can you say that once more?
This result also applies to the linear program.
Does this apply to linear? Yeah. So this is really the class of functions is a piecewise linear class of functions. So in that sense, I guess like it's really like this is for even an unconstrained problem. but it's not a linear, like the optimization problem is not a maximization problem. So it's not really, it's not like the class of functions that we construct. Maximization is not just a linear function, even though it's a constraint. We don't know the answer for linear programming. No. Yeah. Yeah.
So if the lower bound is that one, how did he go big? Lower than
Extra assumptions.
Oh, okay, okay.
Under some more assumptions, you can prove a stronger bound. Yeah. Okay. And there are a lot of interesting questions here. I think extending it to other classes of functions like linear programming could be one. You could also, like there are, like even in these bounds, there are certain things that we don't know. Like we don't know what happens for randomized algorithms in certain settings. But more generally, I think like would be very interesting to understand what happens for like additional structures that we usually assume in optimization, or which are common in optimization. For example, smooth functions or smooth strongly convex functions. Like for these smooth strongly convex functions, do we need things which, can there be things which do not depend on condition number? This is something I'll talk about more in the next part. In particular, I think like even from like the perspective of practice, like where you usually use these memory efficient techniques, like one question is if we can do something better than gradient descent without like while still using the linear memory which gradient descent uses. Can you improve on the gradient descent convergence rate? And especially in regimes maybe where you're looking at very small errors. So gradient descent, the convergence rate depends polynomially on 1 over epsilon. So it would be very large if you're looking at small epsilon. Is that necessary or not? Broadly, I think that I think it's not possible in general, that we cannot improve on gradient descent convergence rate without using quadratic memory. It goes back to this like dichotomy that I was talking about in the beginning. It seems to be like in the algorithmic landscape, there seems to be nothing in between, at least as far as I can see.
It's like for this you're very small epsilon, like do you know of algorithms that outperform gradient descent?
It's a good question. So there is in one very extreme regime, like there was a paper maybe a year ago or so, which for like if you're looking at epsilon, which is exponentially small, then you can outperform gradient descent. Actually, it doesn't even outperform gradient descent. What it does is that it gets the convergence rate of these cutting plane methods with a little less memory. But that's in this very extreme regime. But even there, yeah, like it's still it's using super linear memory. It's not working with linear memory. Yeah. Yeah, so there's not that much, which I think it would be interesting to see if there is something in between. Like, so algorithmically, there's not really, there's the space here. There could be some algorithm here, but we don't know of it. And maybe there isn't. I'm not sure. Okay, so let me talk about one other setting now. Like, again, continuing on the same line of work and going towards this broader goal of understanding optimization with memory constraints. So we'll talk about stochastic optimization and how we can use some of these perspectives to understand how trained transformers solve certain problems like linear regression in an online setting. So stochastic optimization really is like what we do in practice machine learning. We can't really get the full gradient. So usually we'll estimate it by sampling a batch of data points. We talked about, Pranay talked about it, I think earlier and in his talk, or was it you? I think some talks we did discuss stochastic optimization. And you can ask the same question here, like what is the trade-off between the available memory and the number of samples that you need to optimize here? So if you have samples coming in from some distribution, and if you're memory limited, is there a trade-off between the number of samples that you need and the amount of memory that you have in order to solve the optimization problem? And I think the simplest setting to understand here, this is just in the setting of a linear model. So suppose you're just solving a linear system, Ax equals B. You're getting these data points one at a time. So this is an example in 2 dimensions. You're getting A1, and then you're getting the inner product of A1 with this unknown vector X that you're trying to find. This inner product is B1. So you get A1, B1, next time step you get A2, B2, and so on. And we're looking at this in the streaming setting where you get these data points, And at every time step, you can get a new data point, but you cannot go back to the previous data point unless you store it in memory. So it's like we're trying to understand if you're limited in terms of your memory, if you cannot store a lot of data points, then do you end up needing more data points in order to solve the problem? So that's a setting, and we can consider different, like we look at again the number of bits of the algorithm as the metric of as the amount of memory, and you can consider different distributions from which these A's are sampled. We'll consider like Gaussian distributions typically, but even over there you can consider different structures on the covariances, which I'll talk about a bit. You can just think of it as being standard Gaussian for now in order to understand it. So what can you do here? If you have enough memory, you can just store enough data points and then solve the linear system, right? So if you're in D dimensions, you store D examples, and then you just solve the linear system using your favorite algorithm, say Gaussian elimination. You get your answer, you solve the system. So in D dimensions, you only need D examples, but you are storing D examples, each of which is D dimensional, so you need D squared memory. If you wanted to do this with less memory, again, you have gradient descent. That's our main technique. You initialize, you keep running your updates, iterates over each and every example that you get. You take more examples, but you only use linear memory. How many more examples? It depends on the structure, and it depends on how nicely behaved your distribution over examples is. In this case, where the examples are coming from this isotropic distribution, you only need like D log 1 over epsilon samples in order to find an epsilon accurate point. But you need a lot more when things are not as well behaved, in particular for these ill-conditioned settings, which I'll talk about in a few minutes. Yeah.
Also, one could run many different programs and try to estimate.
Yeah. So you could run, like, for example, a different step size or like different variants of gradient descent or.
Assuming you're running A minus B.
Yeah. I see. So if instead of like squared, if you run on absolute loss, I don't think you don't get a better convergence rate than this. So you, for example, you cannot. It doesn't seem like you can still solve the problem with the same sample complexity as say Gaussian elimination. But it would be interesting if there was a setting in which that did help. Yeah. Yeah. Yes.
Setting, right? So Gaussian elimination shouldn't work, right?
Maybe I'll talk about that a little bit more. So maybe let's hold on to the ill-condition setting for a minute. You'll need a few more samples, but it won't be as bad. But we'll get to that. Okay, so essentially here, if we go back to this kind of axis again, so we have memory and we have data, then Gaussian elimination, it requires like D squared memory, but a lot less data, like D, but like I'm ignoring some constant factors here. And it'd be a little bit more for ill-conditioned settings, but not that bad. Gradient descent, only linear memory, but more data. And then again, like you can do everything over here trivially, just by wasting memory or wasting data. But we want to understand if there's something in between these two, like what are the points which are algorithmically feasible. And more generally here, like what we're really looking at is trying to understand a distinction between first and second order techniques. So gradient descent is a first order technique. It just uses the gradient information. Gaussian elimination, you can think of it as a second order technique in the sense that you're just solving the linear system. You're using the full Hessian information. And like these, like first and second order techniques they're kind of like the two main class of techniques that we have in optimization. First order techniques are way more popular because they are much more efficient. They only need gradients. Second order techniques, they are usually a lot more expensive in terms of like memory, because you need to, like for example, Gaussian elimination, D squared memory, or in terms of the running time as well. And for that reason, they are not as popular, even though they can get much faster convergence rate. And like in general, like even if you look at like practice of optimization in machine learning and in LMs right now, there is a lot of like effort in trying to use some second order information in order to speed up convergence without incurring the full cost of second order optimization. Like I think the simplest ways are like these adaptive gradient methods like Adam and so on. But then we also have like these like newer techniques which try to use a little bit more structure. We can talk about it offline if you're interested. And we want to understand if there's something in between. In general, like it doesn't seem like there is. Like so, for example, you could ask if there is some kind of 1.5th order method which maybe uses D to the 1.5 memory. And doesn't seem like you can do that in general. Again, like this a conjecture again that seems like in order to improve on these best known convergence rate, you need a lot more memory. And this gap, like again, if you look at this figure, what this really says, the conjecture is that there's not really that much in between the two. That if you want to improve on the convergence rate of say gradient descent, you really need to use a lot more memory. You can't really, there's not as much benefit in using like d to the 1.5 memory. You only really get the benefit if you use a lot more memory. So this memory in some sense like determines the best sample complexity that you can get. If you have enough memory, you can use the second order method, get a faster convergence rate. Otherwise, you must suffer from the first order convergence rate. Oh, yeah.
So the first order method also uses the amount of data or
The amount of data as well. So in this particular case, so if we look at like this case where the data points are coming from this nice isotropic Gaussian, then the first order method, as you said, it uses d log 1 over epsilon data. So the distinction is d log 1 over epsilon versus basically d. So it's only in terms of the log 1 over epsilon. So the gap is much smaller there, but there's still that gap. And this gap is larger if you look at ill conditioned settings. So maybe let me get to that now. So if you look at these ill conditioned settings, like these first order methods, they need a sample complexity which depends polynomially on the condition number. What is the condition number? For a linear system, it's just the ratio of the largest to the smallest eigenvalue. If the condition number is large, it basically means that there are certain directions in the optimization landscape which are really flat and certain directions which are very sharp, which makes things hard for like first order optimization techniques because you can't really choose the right step size. If you choose it to be too small, then you just won't make progress along this flat direction. If you choose it to be too large, you'll be oscillating too much along the sharper direction. On the other hand, like second order techniques, they can essentially correct for the curvature. So you can use the Hessian information to correct for the curvature and make the problem look much more like a nice rounded bowl, and you still get those fast convergence rates. So essentially, these first order techniques, you need a sample complexity which depends polynomially on this condition number, at least square root kappa, that's the best we know. Whereas you can get a logarithmic dependence on the sample complexity in terms of kappa. So you can get something like polylog kappa if you are using second order techniques. So to answer your question, if you look at Gaussian elimination, the samples are coming from an ill-conditioned distribution. Actually, for Gaussian elimination, I think even a constant factor would be fine, but definitely d log kappa samples would be fine because the matrix would be well conditioned because the eigenvalues, they all concentrate, like it's like random matrix theory for Gaussians. It concentrates very nicely. So second order techniques need a lot less samples. And again, yeah, I think it would be very interesting to understand if there is what trade-offs there are between these two. I think that there is again some kind of dichotomy here that for at least some class of linear systems, you need either quadratic memory or you need to suffer from a sample complexity which depends polynomially on the condition number. So yeah, I think, yeah, so I don't have the answer for this. The reason I think this would be very interesting is it would kind of say if what we are doing right now in deep learning, is it optimal? Is it the best we can do? And like we use these optimization techniques, these first order techniques, and we can't really afford to use like full second order techniques like quadratic memory that if you're looking at